All right. Now we're ready to go. So, evaporative cooling, the factors that affect it. We need to know how we can use evaporation to remove heat from a substance, or if we want to prevent it from occurring, how we can change those factors. Temperature, surface area, and humidity. The Coolgardie Safe, perfect example. As you do past tests, you will see examples of evaporative cooling, and you'll see the solution, the required solution. Now, next, I need to speak about an effect that occurs when you compress a gas. And this will help us understand how refrigeration works. So, I need you all to follow my lead here. We've got to really consider conservation of energy, which then leads into laws of thermodynamics. So over here we're going to write work equals the transfer of energy, which is energy final minus energy initial, which we can write as F times S. Okay? Now what I want you to imagine over here, I've got a piston and a cylinder. So we've got a volume of gas particles in this piston, and I'm going to now apply a force over a distance. So imagine, and it worked a lot better when I was using notability, imagine that I push this piston down, right, and compress the gas. Now, in chemistry, you might learn the gas laws that P1 V1 over T1 equals P2 V2 over T2. Have you heard this equation being uttered in chemistry? Yes? All right. So, if we keep, well, actually, we're not going to keep temperature or pressure constant, but if we squeeze a gas, we're doing work. Literally, I could apply a force meter to the top of that piston, and a gas wants to exist at a standard atmosphere. If I now suddenly try and push it down, I'm going to apply a force. And in fact, the force actually increases over time, but force times distance, I could quantify how much work I have done by pushing a piston down. Okay, now conservation of energy says that if I've done work, it has to have gone somewhere. Well, it turns out that this transfer of energy goes into heating up the particles. Providing that they don't change phase, it's going to go into an increase in temperature. So literally, as I push down on that piston, the temperature of that gas increases. So the energy has gone to the kinetic energy of the particles. Okay? Another way to look at this, and it's quite an ingenious way if I don't say so myself. If you have a particle hitting the surface of that piston with a certain speed, an initial speed u, let's start over. If it hit just a stationary surface, then it would travel off colliding elastically with exactly the same speed. It would just bounce off it like a bouncy ball. However, if this container was now moving down, right? So now you have to imagine a bouncy ball hitting something that's approaching it. Boing! It's going to recoil back into the system or back into the volume with a greater speed. Boing! Like that. Okay? And so that is the repulsive force that you're feeling. As you push down on this imaginary piston and compressing this gas, the force that you're feeling is actually the momentum of the gas particles striking that piston. And so if you push it down, now follow my logic here. If we push this down, it now gets hot. Okay? So I've now got a really, really hot gas that's sitting in this vessel. The vessel gets hot, the metal gets hot, it then starts to lose energy, and we'll look at the processes at which it radiates heat out. There might be some convection going on, there might be some conduction. That, if it is hotter than its environment, heat will flow away. We learned that. Heat will flow from a hot object to a cold object. So now what I've done is I've set up a situation where the environment is colder. Environment is colder than the gas. And so what happens is that Q will say, see you later. Heat flows out. Okay? So again, you need to use Mr. Imagination Land here. I hate this. This is carbon dioxide, not nitrogen dioxide, calm down. So CO2 canisters. You would have played with these if you made your CO2 drag races in D&T. Yes? Right? Now, when these were made, they forced a whole lot of carbon dioxide into a small volume. And when they would have done that, this would have gotten incredibly hot. Ooh, hot, put it down. Hot tomato, hot potatoes. It eventually cooled down. Let's just leave them on the shelf for a couple of days. Cool down CO2 canisters, and the heat wafts off into the environment and eventually cools down. But they're still under pressure, right? So now what happens is if that, how can I explain this? If we were now allowed to expand that volume back out, the reverse process is going to occur. Now, the particles do work on the system. They lose energy. They cool down. The analogy here, imagine that you were a bouncy ball, not striking an approaching wall, but striking a receding wall. They would recoil back into the container slower. Their kinetic energy would drop. Their temperature difference would decrease. Okay? This is known as the gap effect. Same deal. Here I have some pressurized gas. Oh, Jesus. Don't know why that. There's, in fact, watch this. Ready? What's going on there? I don't know. Anyway, when this was made, don't worry, it's not flammable, so you can smoke when you you can use this to blow dust out of computer circuit boards, and it's actually, it can be used to cool things down. When this was made, a couple of things happen. It turns into a liquid. So under pressure, it's a liquid, and it would have been a very hot liquid. When it was pushed in there, you bloody get in there, it would have got really, really hot. Let it cool down. All right. The pressure still stays. When it cools down, it's still under pressure. When it is allowed to expand into a larger area, literally they collide with less kinetic energy. It cools down. So you can basically freeze. You can actually freeze and get ice forming on the table here. Oh, it's cold. Give myself a frost burst. This is what those idiots do. Was it Frosties? With deodorant cans? Yeah, idiots. Look, so I've just managed to freeze that entire section there. I hate doing this, but I'm just going to run this. Now, would you agree, if you could just see that, we're at 24 degrees? Yeah, 24. Now, that's got a little thermistor that's attached to the inside of this wooden block, and in here is one of these CO2 canisters, right? So I'm going to allow this pressurized gas at room temperature to expand, and I hate doing this, but here we go. Who did the CO2 canisters? How do you pop them? How do you pop the CO2 canister? A pin? How do you pop them? With a pin? Like one of them? Yeah? See, I don't like, here we go. How hard do you have to hit it? Yeah. Oh! Alright. No, it didn't. It went down. It's going down. It's still going down. Still going down. There's a bit of a time lag, but we went from 24, we're now at 22. That was very boring. Much decrease. Many wows. Still going down. Not quite sure whereabouts in there, but anyway, we get the expanding. That's called the gap effect. And catch, throw it around. Throw it quick. Throw it quick. Pass it around behind quick. Yep. Yep. Hold. Yes. Okay.
Makes sense. Everything makes
All
sense.
right.
Why is it called the gap effect?
I'm not too sure. Because I guess you could treat the particles now jumping into a larger volume, and so it's now going to, as it expands, it's kind of like the expanding universe. As it occupies a larger volume, the temperature drops. All right, just hold on to that, please. Whoever's got it. Now, gentlemen, shh. Listen up. This is the gap effect. We need to understand it because, again, it's used in refrigeration. It's an effect occurred when a pressurized gas is allowed to expand. It essentially does work on the system. So the system can do work on the gas. That would be me pushing the piston down and it gets hot. It gains energy. If we go in reverse, the gas can do work on the system. This is important because you have Q is either going to be positive or negative. When I push the piston down, it gained energy. Its Q value was positive. I did work on it. I transferred energy from me to the gas. In the reverse, the gas does work. So obviously when it went shh, it pushed a whole lot of gas particles out of the way. Right? And it expanded out into space. The energy left it. Its temperature dropped. It did work on the surroundings by pushing the gas away. So as a result, it lost internal energy. It lost kinetic energy. As it travelled outwards, it slows down. There's so many ways you can imagine it. Remember, they're colliding with themselves, with their neighbouring particles. And all of a sudden, if the space that they're occupying starts to expand, then their relative velocity of approach starts to reduce. And when they collide, they're colliding with less energy. It seems a bit weird, but as they occupy a larger volume, their temperature drops. You might sometimes see this. Q is removed from the gas, temperature drops. If you have an LPG barbecue gas bottle, has everyone seen a barbecue gas bottle underneath their barbecue? Yes? You might notice, and it only really appears on a humid day when there's lots of moisture around in the atmosphere, you might see frost occurring either at the bottom or at the top of the gas canister. And that is the gap effect. As the liquid pressurized fuel expands into a gas, the gap effect, it gets very, very cold. So you actually get really cold gas travelling out. So cold that via conduction, the container gets cold, and then all the water molecules in the air suddenly lose their energy. They condense and then continue to freeze down, and then they cool down, and then they freeze, and then you end up getting frost on the surface. Same as what just happened here when I was able to get frost. I was basically sucking all of the moisture out of the air and causing it to solidify on the table. Now, on this, obviously there's a lot more going on to this diagram. Whoop, come on, change colour, thank you. There's a valve that runs down to the bottom of your gas tank and then goes up and through. And there would be a level. Is it laggy? Oh, well. There we go. You've got gas here that's going to be pushing down and then it draws up into it. So obviously it's under an immense amount of pressure. You've got liquid here. There's a valve at the top that if you open, it basically, as it expands, it turns from a liquid into a gas. Heat is drawn from the substance as well. It's a bit tricky because you've got latent phases as well as pressure. But let's go over the page. Come on, page 4. All right, so have a think. If I can get my container really, really hot, if I can get my gas or liquid or whatever, if I get it much hotter than its environment, well, I have to do work. Okay, we can't get this for free. I have to put some work in to get it really hot. That was me applying a force over a distance to pressurize my gas. It then gets hot. Then let that heat get removed some way into the environment. And then allow that gas to do work on the system. And then it's going to cool down. And so if we can get the cool gas to somehow enter the classroom, we will get the cooling effect inside the room, and the heat that we got rid of is just thrown outside the classroom. So what I've tried to explain is what this thing's doing in the back corner. You've got an external unit of your air conditioner, and you've got your internal unit. Okay? The same is for a fridge. You have the external unit, which is generally at the back of the fridge, and the internal unit are the coils that run through the inside. So, we've got, basically it is a cycle, as the information suggests, it's a cycle of drawing heat from one area and moving it to another. So we're essentially removing heat from this classroom and throwing it outside. But it doesn't want to do that on its own. We have to put work in. So what we do, we compress a refrigerant into a liquid, okay, which causes it to become very, very hot. So not only are we using the gap effect, we're also causing it to change into a liquid. So we get this hot liquid, okay? If we can run this hot liquid through some metal coils, and have those metal coils matte black, which are very good at radiating out heat, we can allow that heat to move away. So when we blow air across it, the heat is drawn away. Now that is going to occur at the back of your fridge or outside the house. So what we're sort of describing here is the hot liquid. If we can draw hot air to very hot air, basically my Q, if we could draw Q leaving, go to the atmosphere. Atmosphere. So here, work is done on refrigerant, and that's at the compressor. So again, that's me pushing down on the piston, causing it to get hot. Then we filter this very hot refrigerant, which is now turned into a liquid. It's really, really hot. We're talking, 60, 70, 80 degrees. It's now outside in the outside unit. There's a fan there that just blows air across it. It might be outside air at 30 degrees, but if you've got air at 30 in contact with hot coils that might be at 70, there's a difference in temperature and heat will be lost. Okay? So now, let's allow the gap effect to occur. Let's bring this slightly, it's still warm, but it's slightly cooler, but still warm. Compressed liquid. At the back of this unit up here, there's going to be an expansion valve that basically lets that compressed liquid expand into a gas. The gap effect occurs, and now we have very, very cold gas here. Okay, so could we please write hot compressed liquid, and on this side we've got cold rarefied, which basically means low pressure. I'll write that a bit neater. Rarefied gas. Okay? So again, inside this unit at the back, there'll be a similar set of coils. It's got a temperature difference, but rather than outside where it's hotter than the environment, now it's colder than the environment. And so as you draw in some air, so some vents at the back of here, we're drawing in some air at the back, coming in warm, in contact with those cold coils, it then comes out cool. And so this is where the Q that was thrown out started in the classroom. So I could have started this cycle here is where the Q from the classroom gets in to the refrigerant. Okay? And then it travels through to repeat the process. So, you know, the 1,000 joules that's removed from the air inside this classroom is the 1,000 joules that's dumped outside. But the only way we can do that is by doing work on the refrigerant to get it to a hotter temperature. Okay? So again, we can't do this process for free. And there are laws of thermodynamics that says you cannot just get free energy. Okay? This is not a 100% efficient process because we have to put in some extra work. We've got to put in a little bit of extra work there. Okay? Now, there is a diagram. In fact, could I just get you guys to do something for me? We've got 5 steps. And you've got 2 diagrams. I would like you to read those 5 steps and write on the diagram number 1, number 2, number 3, identify where those steps are occurring. Okay? So here we have it's exactly the same diagram. Two diagrams showing the same process. I'd like you to identify where those steps are located. Okay? So you can do that at your own time. I'm going to do it slowly. Yes, what's up?
It's just with this being cold and a gas, is that just due to the pressure change?
Yes.
That they can be a gas even though it's colder?
So you see we've got a low pressure, evaporator, high pressure, high temperature. Okay, in this it's not, hang on, condense, liquid, evaporates. Ooh.
It's a vapor in the top left.
Why would this be called an evaporation coil? Ah, thank you. Because I think...
That's what because it's going to liquid if it's...
Well, let's write it down and we'll see if there's any latent phases that might be helping us here. So we've got... Step 1's there. Step 2 is occurring there. Step 3. So have a look. The volatile liquid. So we've got 2 things happening at step 3. You've got a liquid that's volatile. It will readily turn into a vapor. And we experience that effect when we drip the volatile liquid on our hand. We could feel the heat. It needs a certain amount of energy. It takes it from its surroundings. Where do you think it's taking it from? It's taking it from the heat inside the air conditioner. All right, so it's saying, look, buddy, I'm turning from a liquid to a gas. You know, I'm doing it. And if you've got any energy, I'm taking it from you. Thank you very much. Okay? So as it expands and goes from liquid to gas, you've got 2 processes. It draws the heat from the surroundings, latent heat of vaporization, and it's now entering a larger volume. So that's how you can get your, you know, these fins in your refrigerator and your freezer can get to very, very cold, providing it's pressurized and providing you have a decent amount of refrigerant going on. Step 4. The cold gas now draws heat from the surrounding air. Well, I reckon that's here, step 4. And if it does so, the warm gas now brought back to the compressor, probably here. Okay. What about this one? We've got the compressor is here. Step 2, we're going to remove the heat. Step 3, we allow it to expand. Step 4 is happening here. And then step 5, it's brought back and the cycle continues. Okay? Cool beans.
Right.
Yo.
Is the expansion valve and the expression valve just the same thing?
Yes. So if you look what's happened, we've gone from high pressure liquid to low pressure liquid, and then where it evaporates turns into a gas over here. So obviously they've spread it out a bit. There are going to be regions, it's going to expand into this coil, but they've just kind of separated it to show you the different steps, step 3 to 4. So yeah, high pressure to low pressure, that's where it's allowed to expand out and the gap effect occurs. Okay? Now, cold environment, hot environment. This is outside on a hot day. This could be air-conditioned room. Or, don't draw this, this could be your fridge. And this is the back of the fridge. If I could spell. So, again, you need 2 separate units. And generally we insulate our fridge to try and keep extra heat coming in. Did I put a picture on? No, I didn't. Oh, really? I thought I had a Simpsons picture. Let me just see. No, I didn't. Damn. I thought I did. Hang on. Give me a second.
In my house, they're both never have
I'm listening. What are you saying? No, something slightly different. Damn it. Just give me a second, guys. I want to search up something.
I have one patty, but so I cut it off, and then I put it into a sandwich What would you do with that patty?
I'm having a bit of difficulty here.
Too much work required. Cooper, I could not be bothered to write at school and get my actual story so I could write my notes. I could not be bothered to do anything else.
Always physics, bro. Always.
That ain't it. No, that ain't it.
Wait, did you drop that box?
Looking at the class,
Whoa. Calm down, laptop. Okay. Sorry about that delay. This is a lovely little diagram that's showing some stuff. So, refrigerators and air conditioners are heat pumps. Remember I said it's a way of taking heat from one region and moving it somewhere else. It will not occur on its own. We have to force it to occur. Okay? So a heat pump, it applies external work to extract an amount of heat from a cold reservoir and delivers heat to a hot reservoir. So this W here, that's us putting the energy in. That would be the compressor. There's a little motor at the bottom of your fridge. There would be a motor outside Petruka's office. You've all seen that big aircon, the external aircon unit. Yeah? Inside there would be a compressor. It's doing work to turn our cold gas into a hot liquid. Okay? So that's the arrow there. Basically, that's the only way we can make our refrigerant, because we can't say liquid, we can't say gas, because it's in different states depending on where it is in our cycle. So we'll call it refrigerant. That's the only way we can make our refrigerant hotter than the environment. All right? The only way to make my piston hotter than the environment was to force over a distance. I had to put work in. Let it get hot. There's our hot reservoir outside Petruka's office, blowing hot air into his office, and he's sitting there sweating. No, it points up the walkway. Then the cold reservoir is the cold coils coming through. Okay, so if we follow the flow of heat, you've got to put work in. We're not really seeing the removal of the heat here, but this is just a diagram to show how it occurs. Without that, this would never occur. You would never have Q going from a small Q to a large Q. Right? That would be just like sitting here with the air conditioner turning off, just hoping and praying that the room suddenly got colder because the outside air suddenly got hotter. That's called reverse entropy. Yeah? Won't ever happen. Reverse entropy is heat flowing the wrong way. Heat always flows from hot to cold. If we sat here with our fingers crossed hoping that the room suddenly got colder, that would be the heat going from cold to hot. Yeah? It doesn't work. The other analogy is putting the ice cube in your glass of Coke, and the Coke suddenly starts boiling and the ice cube gets colder and colder and colder as the heat flows out of the ice cube. That doesn't work. Okay? So that's why you can never have, you have to put work in, right? Something has to be driving this process to make the refrigerant hot and liquid so that it can then waft off the heat to the environment, and then it can come back in and expand and evaporate. Okay? Cool. What else does it have on this page? There's some air conditions and heat pumps. That's an inefficient heat pump energy flow. What's going on here? Whoa, calm down. Natural gas, heat pump from outdoors. Oh. It's conservation of energy. Let's have a look. Primary fuel is coal. Some of it gets sent across as electrical energy to possibly a heat. This is a heating unit, so this just could be an electrical bar heater sitting in your house. All right. If we get one unit in, we might be getting heat from outdoors. Again, remember, it's strange to think that cold air, there is energy there. Okay. Just because it's cold outside doesn't mean that there's not energy present. It combines and away it goes. Some of this energy is going to be dumped into the atmosphere. Again, as we get to the laws of thermodynamics, basically you cannot get all 0.9 going this way, because that means that there would be no energy removed down here. We'll look at, I've got some diagrams of heat pumps on a document that I should have put in our booklet, but it's not present, so I apologise. Let's go back to our booklets. All right. Could we please get to this page? The next page should now be conduction. Okay. We are going to come back to the refrigerator and the air conditioner, but we have to do a little side mission where we look at conduction, convection, and radiation, because there are reasons why we design air conditioners and fridges and freezers the way they are. Okay? So we've got to go back to these. Please recall, from Year 9 Physics, you may have learnt in heating and cooling, there are 3 different modes of heat transfer: conduction, convection, and radiation. This one is where there is no net transfer of matter, but there is a net transfer of energy. Okay? So the objects are not moving. Right? They are staying stationary. This diagram here, we can't really see or visualize, but I put up a link to my Year 9 class. There's the diagram there, and I placed a link up here. There we go. If you can understand this animation, then that's pretty much conduction done. Okay? So, have a look. We start off with our lump of metal at the same temperature, we apply heat to one side, and via internal elastic collisions of the particles, the kinetic energy is transferred through the material. All right? They're colliding, like Newton's cradle, the little stainless steel balls that collide and impart momentum. Pretty much the same process, but on a much larger scale, lots of atoms colliding. Eventually, this continues until there is no net transfer of heat. What do we call that temperature? Equilibrium. So this will continue happening for as long as there is a difference in temperature. There will be a net transfer of heat. Okay? So, back to our booklets. What are we going to write? On my little diagram, heat transfer, conduction. Where's my pen? There it is. Okay, so we'll go lots of EK here. We will say high temperature. And then on the other side, less EK, low temperature. And we would see over time, have I run out of pens? I'm going to add a pen. There he is, thank you. Via collisions, they're imparting their kinetic energy. Okay? So it's the internal elastic collision which imparts or transfers kinetic energy. Okay? I just want to write here, this transfer of heat over time will occur as long as there is a difference in temperature. Okay? So, now going to pretty much some chemistry here, talking about... Sorry, question? No? Statement?
Oh yeah, it's just the lower
Time. The rate of change over time. So how quickly we can transfer in a given time period depends on the difference in temperature. So, we know that some materials are better at transferring heat via conduction than others. We call them thermal conductors. If they are not good, we call them insulators. If you are a poor conductor, you are an insulator. It comes down to whether you have free electrons or not. If you have free electrons, so these free electrons can assist in bashing and transmitting and imparting EK. Now the collisions, basically it's an electrical interaction, Alright? So as you take jiggling electrons, they can make other electrons jiggle if they are free to move. If they are locked in a chemical bond, like covalent substances, any of these windows open? So if you are a non-metal, then you're normally a covalent bond. Those electrons are busy. They're like, sorry, I'm locked in, I'm not moving. But the electrons that are spinning around the metal atoms, if they suddenly go whoosh over here, then your electrons move, then your electrons move, everyone's electrons move in this ripple. Alright? So it comes down to whether it's just the electrons, whether it's the nucleus moving, jiggling backwards and forwards, and the electrons, or if it's just the nucleus. The nucleus is not as good as imparting its energy because it's stuck smack bang in the middle and doesn't really interact with any nucleuses near it. But the electrons that are in the valence shells, they can just jump across and transfer. Okay? Yes?
Is my hand on the desk?
Yep. And guys, don't be silly. Don't be silly. Let's take that. Your surface temperature of your hand is about 35. The table is at about 24. So you've got about 11 degree difference. If you left your hand there, eventually the table surface will get to 35. And if you've got a 35 lump of flesh on a 35 lump of table, there will be no net transfer of heat. Okay? If you move it to a cooler part, then all of a sudden you feel the heat being drawn from your hand again. Over the page. No, not over the page. Back here. How long have we got? 5 minutes. The rate, or dq by dt, or delta q on delta t, depends on a number of factors. Now you may have learnt this equation in year 9. So first off, the difference in temperature. It's proportional to difference in temperature. Now this is going to be T hot minus T cold, one object minus the other. So it's not final minus initial, it's what's that temperature and what is this temperature? Is there a difference? Okay? A greater temperature difference means they're bouncing around with more kinetic energy. They're going to lose that energy and impart that energy at a greater rate. Next, Zach and Will. Yes?
What's the symbol?
Proportion. So if we double delta T, if we go from a temperature difference of 2 degrees to 4 degrees, we double the rate. If we go from a difference of 2 to a difference of 10, then the rate goes up by a factor of 5, because we've gone up by a factor of 5. Next, the thickness of the material. This one is an inverse. Oh, hang on, let's just stick with the triangles. A thicker material requires a greater number of molecular collisions. It's going to take longer for our kinetic energy to get from one side to the other if it has to bash into more atoms. Okay, so that's an inverse. L is, we'll look at the factors in a moment. L is the symbol for thickness. The thicker the material, the slower the rate. So if we increase the thickness of the material, it slows it down. If we go the other way, if we make the material thinner, then it's going to pass through at a greater rate. Increasing the surface area increases the number of particles involved in the collisions. This is almost like your collision theory in chemistry. The more particles that are free to interact. And then lastly, we've got this constant of proportionality called K. Okay, so delta Q on delta T, proportional to some constant that relates to the substance. So I will highlight I've run out of highlighters. Blue. Okay, so those are the 4 factors. If we combine them all together, we've got K, A, delta T divided by L. Okay? And that is Q on T, which is power. So really, this equation is the power of thermal conduction. How quickly heat can be drawn through a substance depends on the temperature difference, the surface area, the thickness of it, and what it's made of. Just quick little side mission. If we wanted to rearrange for K, well, what have we got? We've got Q on T equals Ka delta T over L. So follow my lead here. To get K on its own, I'd have to multiply by L and then divide by A delta T. Okay? Now, just to make things worse, Q over T is called a watt. So I'm going to just call that a watt times L divided by area, which is meters squared, and delta T is in Kelvin. Yes, Matt?
Power times L over.
Yes. Yes, but I left it as Q on T. But yeah, you're right. You could just write it as power. So it could have been power times thickness divided by area delta T. But I'm just going to leave it for now as Q over. Now we get that meter cancels with that meter, and so the units come out as watts per meter per Kelvin. Which, down on our next page, we've got some common substances. So could we, once we've finished writing that, could we turn over the page? And I will stop talking soon. Just have a look at these thermal conductivities. I'm going to slice a line about here. No, I'm not. I'm going to try again. I'm going to slice a line about there. What do you notice about the substances above? Yep. They're all metals. All right, so all of our conductors, basically if you've got a large K value, you can transfer heat at a much larger rate. The ones below are going to be our non-metals, and they are insulators. Okay? Yes? No, so this is not specific heat. This is not a mixture. This is if you've got a substance and looking at how quickly heat passes through it. And you can basically compare the K values. So literally, aluminium can transfer thermal heat 4 times faster than steel. The rate is 4 times greater. So for every second, you're going to get 4 times more Q being transferred. Okay? We shall leave it there. Apologies for just talking non-stop at you for 50 minutes. But we've got to get you guys ready for the test. I will put this lesson up for YouTube, but it's not the greatest lesson because it's me umming and ahhing for a whole bit. Alright guys, the physics help session is in this room if you want to hang around and get some physics help. Otherwise, I'll see you later.